So my name is Rachel. I'm the co-president of Machine Intelligence Community. If my Evert wants to introduce themselves.
Hi, I'm Tyrone, the other co-president of UMIC.
Hi, I'm Devin. Guess I'm technical lead. Um, so yeah, looking forward to a good year with you.
I'm Chloe. I don't know my title. I don't think I ever had one. It's good to meet all of you.
Julius.
Hi, I'm Julius. I'm the web developer.
Okay.
So I'm Charles. I'm the treasurer.
Hi, I'm Dream. I'm social media.
Okay, cool. So that's everyone. First, I wanted to just welcome you all to our community. I'm really glad you guys are all here. Thank you for following up with us from Splash or our email list or however you found out about us. So first, I'm going to start a little bit about who we are. So the Machine Intelligence Community is actually a group of communities in the Boston area. So that's Harvard, Tufts, MIT, and us. So we're an organization focused on providing opportunities for students to learn about machine intelligence in a community environment. So a couple years back, MIC was founded, inspired by the AlphaGo challenge. If you haven't heard of this challenge, DeepMind, if you've heard of them, they're a spinoff from Google. They created this machine intelligence system that was designed to beat a game called Go. Go is a much more complicated game than like chess or checkers. It requires a much more intuition and thinking forward, and it was a real challenge for a machine to beat this game, especially against a very skilled human. So 5 days later, this machine actually ended up beating the best Go player in the world, Lee Sedol. There's a really good documentary about it if you're interested. And then later that year, Rocket AI was founded, and then MIC was brought across the river to BU, where we were officially founded on September 8th of last year. So this is our second year as an established community chapter. That's a picture of us. It's kind of goofy. Sorry for the filter. But yeah. So MIC was founded on 3 core values. Openness. We believe that machine intelligence knowledge should be available for all people. So that includes disseminating knowledge and resources about machine intelligence. Education. Through these workshops, where our goal is to educate you about machine intelligence, obviously. So distilling that knowledge and teaching it to you in a friendly way. And then community, connecting with like-minded peers. So that means throughout these workshops, we want you to sort of interact with each other, to start your own deep learning projects, and with us also, so we can all share our experience. So the goals of this workshop series, this is actually the first workshop of a series we're doing, if you're not familiar. So we're doing the Fundamentals of Deep Learning series. This is the first workshop. So our goals with this workshop are mostly to introduce the field of deep learning and sort of gain some familiarity with terminology, history, concepts, technical skills, reading research papers and current events that come up in the press. Speaking of research papers, we'll probably have a workshop where we teach you just like how to read a complicated looking research paper, which will lead into more paper discussions from papers that are released in the field of deep learning. As I mentioned before, meeting others who are interested in machine intelligence and developing a skill set to start your own deep learning projects with each other, hopefully. So here are the workshop topics. I won't go through all of them, but obviously machine intelligence, you're here. I will give sort of a brief overview of what machine intelligence is. Hopefully this is accessible to all skill levels. And then as we go through the workshop series, our goal is to sort of get more refined and detailed in different fields of deep learning. So neural networks, for example, transfer learning, reinforcement learning, evolutionary algorithms are sort of all like topics within deep learning that we want to get more low level into. But this workshop for now will be very high level, just an overview. And then next week, we'll do some mathematical foundations in deep learning because it's very important to understand sort of the math underneath before we start implementing these really complicated neural networks. So kind of jumping right in. So you probably heard in the press these terms like AI, machine learning, and deep learning, and how they can be used for industry and take over the world and all these things. But these terms aren't really interchangeable. So I wanted to just sort of clear up the difference between these three and where they fall in sort of the field of, I guess, AI overall. So what is artificial intelligence? I Googled artificial intelligence and clicked on images, and this is what came up. So often the perception of AI is that there are these very like complicated human-like robots that are sentient and can bring good and evil into the world depending on their intention. This is sort of a perception that more aligns with something called artificial general intelligence, which basically it's a goal of many researchers, but that's basically saying that these robots are sentient and can have basically any human capability. But I wanted to let you know that we're not there, and we're not close to there. So what actually is artificial intelligence? So it has a lot of different definitions, and as the years go on, these definitions change and morph depending on sort of what's succeeding at the moment. But there's a textbook called Modern Approach to Artificial Intelligence. I recommend it, but it sort of introduces these 4 perspectives or definitions of artificial intelligence. So the first one of these is thinking humanly. So that means having sort of the cognitive capacity of a human. So a machine that is capable of thinking like a human would and making decisions and problem solving or learning how a human does. The next one of these would be thinking rationally. So actually the computations that lead up to deciding based on reason. So as humans, we don't always make decisions from reason. We kind of just, But this is more of a perspective of perceiving, reasoning about an action, and then acting based on what seems most rational at that point. Then the next 2 are sort of based on like how they're outerly perceived, these artificial intelligence agents. So acting humanly, how a human would behave on the outside. So doing things that humans would do, basically. And then the next one's acting rationally. So acting or behaving on the outside based on reason. So again, humans don't always act based on reason, but that's actually saying more of a perspective of intelligent agents that always reason before they act and behave that way. So, for example, consideration of others, having a certain goal but avoiding objects in the way, things like that. So, what is machine learning? Machine learning is sort of a subset of this artificial intelligence, so kind of narrowing in on how we actually achieve things like this. So machine learning is basically learning behavior from data. The term was coined by a man named Arthur Samuel in 1959, and he explains it as a field of study that gives computers the ability to learn without being explicitly programmed. So this is more using applied statistics to estimate very complicated functions for a certain task. The important thing about this is that it's data-driven. So humans learn based on data, like sensory data, things we learn in school, etc. So machines also learn that way. And the important thing about machine learning is that usually there's an element of prediction. So if I learn based on a lot of images, I can predict what object is contained in an image or something like that. So machine learning, learning behavior from data. So then where does deep learning actually fall here? Deep learning is more of a subset of machine learning. So it focuses on the learning algorithms that are modeled after actual neurological connections in the human brain. So it's loosely modeled after like neurons, basically. How in your brain the neurons connect and think, and how we can model that mathematically. So that's sort of a subset of machine learning. So machine learning is basically all these learning algorithms where you can learn behavior from data, and then AI is this sort of big umbrella that encompasses both of those things. Okay, so like I said, deep learning is based on neurological connections in the brain. So if you've seen any model of the brain, it's very complicated. Just like these things, you may or may not have seen this, but these neural networks look like very densely connected, and there's lots of things being passed back and forth to each other. And this is definitely an accurate representation of deep learning. This is what it ends up being. But what it actually boils down to is a heck of a lot of math. So that we use calculus, linear algebra, probability for prediction, right? Optimization theory to sort of correct our errors, and learning theory. And I won't go into any of the details of any of those things, but in next week we'll go over like the math portions of things and how they fit into actually deep learning models. But just letting you know what's coming. So a little history on deep learning. Like I said, it originated from scientists being interested in how biological neurons can be modeled mathematically and how we can make machines think intelligently by mimicking those connections. So in the 1940s, these scientists, Pitts and McCulloch, released a paper called A Logical Calculus of Ideas Immanent in Nervous Activity. And basically, they claimed that neural networks, their idea of a neural network can simulate any machine with like a logical function. So like and, or, XOR, those things. And eventually, a scientist named Frank Rosenblatt created the perceptron that was modeled after this theory. And it looks like this. So basically, we have a bunch of inputs. We have weights that sort of emphasize the importance of each input. Those are all summed up. And then there's an activation function. So Pitts and McCulloch basically said, okay, a neuron either fires or it doesn't. So if you have all of these inputs and their importance and you sum them all up, and if they exceed this threshold, the neuron fires. If it doesn't, then it doesn't. And that's basically what this was modeled by. But so this obviously created a lot of interest in the deep learning community, like using these perceptrons to estimate functions and basically try to do things that we could do. And in the meantime, Alan Turing is defining the Turing test, the criteria for an intelligent machine. And then after this, a man named Marvin Minsky was very skeptical of this whole perceptron idea. So Pitts and McCulloch's theory was a very general theory, right? Neural networks can simulate any function. So Minsky tried to basically simulate a particular machine that could solve a particular task. And he released this book called Perceptrons that basically debunked this whole perceptron thing, basically claiming that it was only a linear function, right? Because it's either firing or not firing. It's only summing all the inputs. So it's just a linear function. How is it supposed to estimate all these complicated functions? More specifically, he gave the example of like counting the number of counting the number of objects in an image. So since there's no like circular component in this perceptron, how is the neural network supposed to go back and actually count, right? So he released this paper destroying the perceptron essentially, and after that, kind of the research in neural networks died down a little bit. But in 1986, Geoff Hinton released his paper, Learning Representations by Backpropagating Errors. So this paper was basically a way to go back and adjust these weights, how important each input is, as it sort of released all these possibilities of how we can go back and adjust our errors and improve our machines. And then, same guy, 2006, he released Deep Belief Networks. This is a pretty cool paper because it was basically the first deep learning architecture with lots of hidden layers. So this perceptron thing only has one neuron, right? So basically he created a network that had tons of neurons and tons of layers of neurons. So like in your brain, signals are passed to other layers of neurons, and he basically simulated that in the deep belief nets. And from then on, it sort of skyrocketed into how we can adjust this deep belief net for different purposes and different architectures that we can use. So an example would be the ImageNet classification challenge. So back in 2012, there was this huge data set called ImageNet. You probably have heard of it. It's like millions of images all labeled with their corresponding class name. So if there's a picture of dog, it's labeled dog, etc. And basically the challenge was to get the best accuracy you can on this data set. Like have your neural network predict the right answer the most often, basically. And it actually ended up becoming superhuman, exceeding human intelligence there. And then a couple years later, Ian Goodfellow released some really good work on unsupervised learning. So I'll go into this in more detail later, but where you're data set has no labels and you try to learn, this is an architecture for doing that, generative adversarial networks. It's pretty popular now, actually, too. And then that leads us to 2016, where we mastered the game of Go. So obviously things have skyrocketed quite a bit. Sorry to bore you with all the history. So this slide is just kind of, where is deep learning? It's literally everywhere, in all the industries. If you Google it, it's like how you can use it for ad recommendation or music recommendation or generation or things like that. So a lot of companies now use machine learning and deep learning in their just everyday process. And that's why it's sort of becoming so important to sort of learn about it. But yeah. Okay, so now that we sort of know the history of deep learning, where it falls in the spectrum of machine learning and artificial intelligence, what actually can machines learn? So we classify machines learning things into 3 different categories of tasks. So classification, regression, and generation. So classification I already touched on, but classification is where your learning algorithm predicts a discrete value, which is a class. So if you have a huge data set of labeled images like cat, dog, airplane, you train your learning algorithm in all these, and then the algorithm predicts this is a puppy based on the labels that it was given to choose from, basically. So a discrete value, a class. So basically we're mapping an input, which is typically represented as a vector, to one class. So a good example of this is the MNIST dataset. So this dataset is a bunch of handwritten digits, and all of these digits have a class. So like the top row is 0, obviously the second row is 1, 2, 3, and they're all slightly different, but they're represented as 28 by 28 pixel images. So when we have our neural network input, these 28 by 28 pixels get broken down into 784, that's just 28 times 28, inputs. So if we go back to this, so each pixel would sort of be an input there. They each get a weight, and this would not be the architecture they would use, but you would put it through your algorithm, and it would learn important features of those digits and try to learn how to predict the class. So yeah. So again, a discrete value we're trying to predict. So another thing machines can learn is regression, where your learning algorithm is trying to predict a continuous real value. So again, your inputs are vectorized. So before our vector was like images, where it was like each pixel was an input. Here we have, maybe you want to predict the price of a house or the cost of your groceries. You could have the features of your house, which come in as a vector, so that you have 3 bedrooms, 3 bathrooms, whatever. And then you pass that through your learning algorithm, and it predicts a continuous real value. So instead of discrete, you now have continuous, where the value doesn't have to necessarily be like a whole number or a class. So yeah. And then generation is a little different. So generative models try to learn and generate the original distribution, like statistical distribution of the training data. So here, just as an example, if you train your model, your generative model, on a lot of Shakespeare, your learning algorithm is going to try to learn the distribution of that data and then sample from that to generate new samples. So on the right, that's not real Shakespeare text, but it's written in the style of Shakespeare because it's taken from the same distribution. So yeah, we'll learn more about generative models in a different workshop. Oh yeah, this is an example. So it's more fun than Shakespeare. But this actually is a joke too. It wasn't actually trained on diners, drive-ins, and dives, unfortunately. But if you were to train a generative model on this type of data, so you take all the scripts from diners, drive-ins, and dives, and you have it generate some script, it should contain sort of the same style of text, same characters, locations, things like that, but not be like the identical data that you gave it, basically. So yeah, I thought that was funny. So now that we sort of know what machines learn, how actually can machines learn things? So learning algorithms, data is very important here, and actually training and testing your algorithm. So there are lots of different types of learning that you can implement in your learning algorithm. So supervised learning is the most popular, where the data set consists of labeled images or whatever you're training on. And basically in that case, it's the case that I was talking about before. So example for ImageNet, you have all these labeled images and you're trying to predict a class given all your labeled data. And then semi-supervised learning is where you have a partially labeled data set. So data is often, in the real world, data is often not labeled. So if I take a picture of a dog, it's not going to be automatically labeled as a dog, right? You have to either have a human label it or a machine or a Mechanical Turk or something like that. So if you don't have labeled data or you have a little labeled data, for example, if you have a very complicated data set that only experts can label, you can have like a little bit of labeled data, have your algorithm sort of learn the important features of the unlabeled data, and then try to have it label, like guess the ground truth labels of your unlabeled data, basically. And then unsupervised learning is sort of the opposite of supervised learning, where you have no labels on your data at all. So some popular unsupervised learning algorithms would be generative adversarial networks, which we'll go over in a different workshop. There are autoencoders, where basically you're trying to have the output be the same as your input, or a replica of your input, and things like that. But even now, it's not well understood unsupervised learning, just because there aren't that many algorithms for it. It's a very difficult task if you have no labels on your data, etc. So then reinforcement learning is where you basically have an agent in an environment trying to learn a task. So it's not supervised learning because you're not necessarily depending on any labeled data. You're placing an agent, like your machine, in an environment, and it sort of has to learn how to do a task with a punishment and reward system. So if I put, usually it's used in, or not usually, but a common application of reinforcement learning is in games. So I'll actually just play the video while I talk. So this is an example of reinforcement learning with Mario. At first, it does very poorly because it's sort of learning as it goes how to optimize and get the best reward, which in this case is getting the best score in the game, without actually knowing how to do it. So it's sort of learning as it goes, and then it gets really good at the end. But yeah. So yeah, we will also have a separate workshop on reinforcement learning, which is really cool. And reinforcement learning also has other applications. Like, for example, you can use it to sort of learn, like if you're recording your screen or something, you can use it for dynamic pricing and things like that of items on a web page, for example, based on like what the user is clicking on. So yeah. And then meta learning, we don't necessarily cover this in our workshop series, but meta learning is learning to learn. That's what it's called, meta, because of that. But basically, meta learning algorithms learn to train other learning algorithms, basically. And it's actually been discovered that they can do that better than humans can, like designing learning algorithms for certain tasks. So yeah.
Computers are better at teaching computers.
Yeah, pretty much. Hey, it makes sense, right? But yeah, and then transfer learning, using learned parameters from a similar task to complete a different task. So if I trained my network on ImageNet, for example, and I had it classifying images, I could try to take that model with those learned parameters and apply it to a similar task. So I could apply it to classification of a different data set, for example, or something like that. So yeah, we'll also have a workshop on transfer learning. So yeah, so like I mentioned before, this is all data driven, right? And deep learning algorithms take oodles of data, like order of 10 to the 5th samples of data usually to train. The reason why for this is not necessarily understood, besides the intuitive fact that oh, well, if it has more examples, then it'll probably learn better. So basically, when you're training a learning algorithm, you usually split your data set 3 ways. So usually about 70%, depending on your available data, of course. But usually about 70% of your data is used for actually training the algorithm. 10% is used for validation. Validation sets are usually used to tune your hyperparameters. So that's a big word. Let me define it. So model parameters are things that your model adjusts while you're training. So in the training set, your model will adjust the weights of the inputs, for example, like the importance of each input throughout the hidden layers, things like that are built into your model and you can't change. Hyperparameters are the things that you can change. So, for example, if you're familiar with like learning rate, how fast does my model train? I can adjust that. How many neurons are in my network, how many layers I have, hidden units, I can adjust all of that stuff. So your validation set is usually used to test like intermittently between training, like am I using the right hyperparameters or what are the right hyperparameters? And this can be configured in a bunch of different ways. And then your test or holdout set is used at the end of your training to test your algorithm. So obviously you don't want to overlap any of these data sets because say I test my algorithm on an image that it was trained on, it has a much higher probability of getting it correct because it was trained on that. But for example, if I train my algorithm on dogs and cats and I test it with an image of a cat that it has never seen before, it is likely to get it right, but obviously less likely than if it were given a cat that it was trained on. So none of these should overlap. And then balance is also important in your data set. You want your data distributed close to uniformly, like the same number, in the discrete case, the same number of classes per set. So, for example, if I were doing like classification between cats and dogs, if I trained on 90% dogs and 10% cats, and I tested on a cat, your algorithm would be much more biased to predict that it's a dog just because of the features that it's learned are much more robust for dogs. So this is sort of like a timeline-ish thingy of how your model is trained. So every epoch that you train, you're iterating over your entire training set, evaluating the loss, backpropagating, going again. So then intermittently throughout this, you're assessing using the validation set, so you make sure your hyperparameters are good. And then at the very end, you have your fully trained network, and you assess it with the test or holdout set, if that makes sense. And the number of epochs you train, it really depends on your model, but it literally can be anywhere from like 100 epochs to like 1,000,000 epochs. So it could take like an hour or a day or a week. You don't really know until you try it. But yeah, this is a general framework for like all models. So I put some references here. These slides will be posted on GitHub, but yeah, if I just put some like things I mentioned throughout this talk, so you have sort of some background. So if you want, you should follow us on Facebook and sign up for our calendar where we have all of our workshops listed out for the rest of the semester. So I mentioned them a lot before, but we have 11 workshops total this semester. They're every week, 7 p.m. Hopefully we will be in the Build Lab next week, but if not, we'll be here. We'll send out an email reminder. This is also a email sign-up list. I made sure it works. It does. So yeah. But yeah, if you want to take a picture of your guide. I think I had something else. Oh yeah. Oh, oops. I didn't finish the slide. I apologize. Let me verbally explain. So upcoming events with us. Next week we'll have our mathematical foundations in deep learning. So math you need to know to get into deep learning and where that math actually shows up in the context of deep learning. So we're trying to not make it just like a math lecture, but it'll be more like an applied, like you get to code and things like that in the context of deep learning. We are going to have a hack night. I don't think we've decided the date yet. But basically, that will be like where you guys can come in and work on your own projects and like mingle and hopefully start group projects with each other. That'd be awesome. Or ask us questions too. And then we will have our first paper discussion soon. But the first one will be on just like how to read a research paper, essentially. So yeah, join us for that. Yeah.
Will the future workshops be at the same like time and day, Wednesday at 7 at this place?
Yes.
So
So
it
it'll
will be at
be
the same time. Most likely, we're gonna have Richard build that just because it has more space.
Okay.
But we'll let you know on the mailing list.
And will always be Wednesdays.
Yeah, Wednesday, 7 p.m.
Okay, Wednesdays at 7.
yeah. Okay. Yeah. Well, thank you guys for joining us. Do you guys have any questions about anything I said? Any gibberish? Okay.
Also,
Thanks,
if you guys, thank you guys for coming. Also, if you guys ever have any feedback about events you'd like to see or things that you're interested in, we're open to suggestions. So
Yeah, come talk to us. We're kind of cool.